This video is going to talk about how to classify chemical reactions, give a few examples, and also show you some pictures of what these things look like for different types of materials. So the first example we have here is two elements combining to give a compound. So this is called combination. That's all it is. Decomposition reactions are kind of like the reverse of combinations. So combination is taking two things and making one, and then decomposition is taking something and breaking it into two parts. They don't necessarily have to be elements, but those are the most common examples. All right, so that's a combination reaction. This one here is a special type of combination reaction called combustion. Combustion is combination with oxygen to form the oxides. So for example, if you take carbon and add oxygen, you get carbon dioxide. If you take hydrogen and add water, you get, if you take hydrogen and add oxygen, you get water. And if you take many other elements, for example, if you take iron and burn iron, you get iron oxide. All right, this equation here with aluminum and iron, and notice how aluminum and iron are trading places in this formula. Okay, in this one, this is iron 3 and aluminum as the element, uncharged. Whereas in this compound, it's aluminum with a +3, and the iron has no charge. It's the element iron. It's the metal. And this is a thermite reaction. This is actually so exothermic, gives off so much heat that the iron you get is actually molten iron. So it says sulfur. That's if you remove the heat quickly enough. This last one's called a double replacement. So this is a single replacement. This is a double replacement. And the analogy I like to use for the single replacement and double replacement, if you can think of these compounds as being, you know, if you have a plus and minus, well, it's analogous to a husband and wife or other couples. And so a single replacement would be basically the, if you were married or something like that, and then somebody would replace your spouse with somebody else, and it would be a new married couple, and the other one would be left out in the cold. A double replacement would be where it's like the TV wife swap, and they never swap two. They always swap two of the same thing so that the combinations afterward are still mixed, plus, minus, or male, female, or whatever. Okay, and so here aluminum metal is replacing iron, which is also a metal, in ionic compounds. Here sodium cations combined with an anion, magnesium cations combined with an anion, while over here magnesium cation is combined with an anion, and sodium cation is combined with an anion. All they did was just swap the ions. So you can think of it either swapping the cations or swapping the anions, the same end result occurs. Okay, so now let's look at the ionic versus molecular nature of some of these compounds. Well, this is two nonmetals. So what that tells us is that this is a discrete molecule with a Lewis structure, like that. I didn't draw the lone pairs on the bromide, but there's 4 of them, which means there's 4 molecules, discrete molecules, and I'm not even going to draw all of them. You can add the bromides to every phosphorus to get the Lewis structures. Okay, that's what the 4 out front means. It means there's PBr3 molecule, a group of 1 phosphorus and 3 bromines, and there's 4 of them, so there's 4. All right, what does 6 Br2s mean? Well, Br2 is a bromine-bromine single-bonded molecule. Again, you can draw the Lewis structure with all the lone pairs, but there's 6 bromine 2 molecules. Now, this is a ratio, of course, right? It's the simplest energy ratio. And I still need 3 more. All right. I don't know if you can see it up top, but there it is. All right, and then finally 1 molecule. Now the structure of this guy is pretty interesting. This is actually a tetragonal arrangement of phosphorus atoms. A little tetrahedron, a little four-sided figure, where the phosphorus atoms. Okay, so now we can see that this is a balanced chemical reaction. There's 4 phosphoruses here. There's 1, 2, 3, 4 phosphoruses here. There's 12 bromines here. You can count 12. And when you count the bromines here, there's 12. That's what it means for the thing to be balanced. So that's what this looks like at the molecular scale. All compounds that are molecules because they're all nonmetals, bonding to nonmetals. All right, now carbon as a solid could be several forms. It could be graphite, could be diamond, so I'm not going to draw that in any sort of detail. The oxygen is, of course, an OO bonded molecule, single bond, double bond. CO2 is also a molecule, like so. Now the textbook also talks about a very important thing that happens. If you don't have enough oxygen to burn carbon, you don't get carbon dioxide, you get carbon monoxide. So incomplete combustion is very hazardous because carbon monoxide is very toxic. You should have a carbon monoxide detector in your house, like I do. All right, so these last 2 examples are ionic compounds, not molecules at all. Okay, so again, this is a metal. It's just a bunch of atoms arranged in a solid. This is an ionic material, so remember it's an iron 3 cation. And there's 2 of them. And there's 3 oxides. So an oxide is an O2 minus. Sorry. It's not a subscript, it's a superscript. Okay. And notice how the total charge is balanced. We have a total of 6 pluses and 6 minuses, and that's why it has to be this formula ratio here. Now, in an ionic material, since this is a solid, they're going to be in a regular pattern, but all the iron 3s won't be together and all the oxides won't be together. They'll be alternating so that they're attracted to their nearest opposite charged neighbors. Again, this is just a whole bunch of atoms and another ionic material, but this time, instead of iron 3, it's aluminum cation, which is always +3. So we don't call it aluminum 3, just say aluminum. And then oxide. And again, it's charge balanced. All right. And so that's what an ionic solid would look like. You know, you can look and find pictures of ionic solids. The last example is dissolved aqueous ionic compounds. Now what happens in an ionic compound when it dissolves, if it dissolves, is the ions get surrounded by water and they're all separated. So you still have the same ions. Not much happens, or most of the time nothing happens to the ions themselves. So for example, if we see phosphate here, it's phosphate here. It didn't change to phosphide or phosphide or anything else. And then chloride stays as chloride, sodium stays as sodium, and magnesium stays as magnesium cation. So all that happens is we have some dissolved ions and some other dissolved ions. We mix them together and they're all dissolved in water. Sometimes when you have ions that coexist in certain pairing, they will form an insoluble salt, and so you get a solid. So magnesium phosphate is one of those substances. So sodium phosphate is completely soluble. When you dissolve it in water, the sodium ions really aren't that interested in reforming the crystalline solid if they're dissolved in water. Magnesium and chloride ions the same. Okay? If they're both in water, then they'd both rather stay in the water. However, if you have magnesium ions and phosphate ions, since they both have a high charge, this one has a charge of 3 minus, this has a charge of 2 plus, they will definitely be very strongly attracted to each other because they have high opposite charges. And so they will clump together into a solid form called a precipitate and settle out to the bottom. And they'll have this formula, again, where the charge is balanced. So I'm going to just write down the magnesiums. And I'm going to go ahead and write in all the chlorides. Okay, one more chloride. Okay, and then again, they're not arranged in any particular order, so I just wrote them down. So, see, 3 magnesium chlorides means there's 3 magnesiums and 6 chlorides, because every one of these has 2 chlorides. So 2 sodium PO4s is 2 sodium phosphates. One of them would be an A+, Na+, Na+. And another one would be another Na+, Na+, Na+. Phosphate, there's going to be 2 phosphates. Okay? So just envision all these ions separated by water. They're all separated from each other. All right, so now let's mix them all together. And now, all of a sudden, magnesium cation can see phosphate. So, let's get together and we'll form an ionic compound where we'll have a total of 6 pluses and 2 3 minuses will make a -6. And so that's why magnesium phosphate precipitates out in this ratio. So the ions will be in a regular cluster and a lattice, magnesium and phosphate, and so on, in a 3:2 ratio. And then what happens to the other ions? Well, the chloride is sitting around dissolved in water and never does anything. And the sodium ions are sitting around dissolved in water, and they don't do anything either. And then we count them up and we say, there's 6 chlorides and there's 6 sodiums. So that's why we write it as 6 sodium chlorides, because this has 6 sodium, 6 chlorides. But it's still dissolved in water because they don't recombine. Salt is soluble in water, so they just stay put. Okay, so this is called a precipitation reaction, which is very common if you take 2 solutions of ionic materials, and one of them is insoluble, but the other one is.